This video is about Lewis acids, base, Ka, Kb, and Kw. Okay, so a revision on Lewis acids and base. Lewis acids is something that can accept a pair of electrons, a lone pair of electrons, and Lewis base is something that can donate lone pair of electrons. So for example, ammonia. So there's a lone pair of electron here. Therefore, it can donate a lone pair of electron. It's a Lewis base. Okay, for acid, say BF3. B has 3 outermost electrons. F has 7. So there's only 6 outermost electrons here. Therefore, there's space to fit in another 1 pair of electrons. So therefore, the base can donate the lone pair of electron. They actually share it in the end. It looks like a covalent bond. And in fact, it is a covalent bond. It's a dative covalent bond. So after they're bonded, all of them would have 8 electrons, while the H would have 2 electrons. So now everyone's stable and octet. And this here is a dative bond. So a dative covalent bond. So without looking at the H like Bronsted-Lowry, the H plus, instead this time we look at the lone pair of electrons. So this makes ammonia a Lewis base and BF3 a Lewis acid. Okay, remember in SL, we mentioned that pH is a measurement of concentration of H plus. So it's not a measurement of how strong an acid is. So a better way to measure the strength of acid is Ka. This is called the acid dissociation constant. Okay, P here will be the same thing as the P in pH. It's negative log. So anytime you see a P, it means negative log. This is how we calculate Ka. So for example, I have a weak acid, say CH3COOH, and I'll add water here. And reversible because it's a weak acid, so it won't fully dissociate. So I'll have H3O plus, and I'll have CH3COO minus. Okay, so the way to calculate my Ka is very similar to calculating Kc. It's just that everything here is in aqueous. So it means that the water is very concentrated here. There's a lot of water, so it remains almost constant. So we're gonna ignore the water here. So I'm just gonna take H3O plus, CH3COO minus, and over the reactants, just like Kc in SL. Now that equals to my acid dissociation constant. Okay, if you compare this with Kc, Kc would be product over reactant, right? So I'm gonna write that H3O plus and CH3COO minus over, so we take the reactants, CH3COOH, and also water. Okay, if you compare Kc to Ka, it looks like Ka is just a Kc multiplied by a H2O. So if you take Kc, multiply by the concentration of water. So if you take Kc, multiply by the concentration of water here, you'll cut it off, right? So isn't it equal to this already? So Kc multiply water will equal to Ka. That is the acid dissociation constant. Okay, as how we calculated pH, we took negative log of the concentration of H, right? So now to calculate pKa, we'll take negative log of Ka. Okay, do you see that in this equation, the more an acid can dissociate, so it'll shift to this side of the equation. Therefore, this will be higher, and therefore, this will be lower. Okay, so if an acid is strong, it dissociates more, then you will get a higher Ka value. If you get a higher Ka value, you will get a lower pKa value. So the higher the Ka, the stronger the acid. These are actually for weak acids. So it's just stronger or weaker weak acids. And your pKa, the lower it is, the smaller it is, the stronger the acid. Next, for base. So similarly, we're going to use the same way to calculate Kb for bases. So these are for weak bases. For example, ammonia. So if this is ammonia, add water, reversible arrow because it's a weak base, so it will only dissociate partially. So I'm going to get NH4 plus and OH minus. Okay, so to calculate my Kb, I'm going to take the products, NH4 plus multiplied by OH and divide NH3. Similarly, we're not going to take the water since the water remains almost constant. So the stronger a weak base, as in the more it shifts to the right, the higher the Kb will be, and therefore the lower the pKb is going to be. So pKb, the same thing, it's going to be negative log of Kb. Next is a revision on Kw, but there are some new information here with respect to Ka and Kb. So Kw, as you remember from SL, it's a constant for pure water. So at 25 degrees Celsius, Kw is 1 times 10 to the power of negative 14. Because H plus is 1 times 10 to the power of negative 7, and OH minus is also the same thing, 1 times 10 to the power of negative 7. So Kw is the H plus multiplied by the OH minus, their concentrations. We don't use units here. So therefore, you take this, multiply another this. So Kw is always 1 times 10 to the power of negative 14. So this is Kw at 25 degrees Celsius. It's already fixed. Okay, so we did learn about pH in SL, but we never really talk about the OH yet, right? So OH can also be done the same way as pH. So pH was negative log of concentration of H plus. Okay, so a new introduction here, POH. Similarly, you will calculate it as negative log concentration of OH minus. That is POH. So now you have two, you have pH and you have POH. You also have Kw here. And let's look at a separate equation. Okay, let's recall a little bit about conjugates. So if this is your acid, ethanoic acid here, so this would be your conjugate base. So I'm going to put the base here, and then you get a conjugate acid here. Okay, so the top system is for my Ka, so I'm going to write that here, CH3, COO minus, and I have my H3O plus over CH3, COOH. We ignore the water for Ka and Kb. And on this side, CH3, COOH multiplied by OH minus, and the base here, CH3, COO minus. Okay, if I take Ka multiplied by Kb, so CH3COO minus, cut, CH3COOH, cut. So Ka times Kb equals to H3O plus OH minus, or remember H3O plus is equivalent to H plus and OH minus. So isn't this Kw? Remember, this is when we dissociate water. So if you have water, you dissociate it, you'll get H plus and OH minus, just a little bit. 1 times 10 to the power of negative 7 of this, 1 times 10 to the power of negative 7 of this. So OH times H plus, you will get Kw. So is Ka times Kb is also Kw. So we have a new equation here. Therefore, we can conclude that Kw equals to Ka times Kb, and that would be 1 times 10 to the power of negative 14 if it's at 25 degrees Celsius. Okay, remember that negative log means P, right? So we had pH already, so I can P all of this. So P, or negative log, Kw equals to, so if this is multiply, when you change it to log, it will be plus. So negative log of H plus, that would be pH. Multiply would be plus, and negative log of OH would be POH. So from here, we get another formula. Okay, in an acid or a basic solution, you know that this can go up and this might go down, or this might go up and this might go down, but it comes back to the same Kw. And we know that at Kw is 1 times 10 to the power of negative 14. Therefore, if you negative log this, that would be 14, right? If you negative log this, you can try that. Negative log this. So pKw will always be 14. So 14 is equal to pH plus POH. So if you have the pH, you can calculate POH, or if you have POH, you can calculate pH. Just take 14 minus that figure. And therefore, at 25 degrees Celsius, pH plus POH equals to 14. Okay, recall that you calculated the pH value for strong acids and base in SL level. Now that's pretty simple because they fully dissociate. So if I were to have 1 mole per dm cube of HCl, I would have 1 mole per dm cube of H plus. You have 0.001 mole per dm cube of HCl, then I would have 0.001 mole per dm cube of H plus. So whatever the mole per dm cube of HCl, that will be the same mole per dm cube of H plus that I would have. But what about weak acids and base? It's a reversible arrow, which means if I have the same 0.01 mole per dm cube of CH3COOH, I'm not going to get 0.01 mole of H plus. Instead, I might only get 0. Who knows, something like that, or even less. Okay, so we don't know. So how are we going to calculate the pH for a weak acid or a base? Then we will need to use these systems. And that's when Ka and Kb comes in. Okay, let's look at how weak acid dissociate here. It's a reversible arrow here. So it's something like how we work out Kc the other time. But this time, we're using weak acid here instead. Okay, so the initial, let's say it's a certain concentration, and the change is a certain degree of dissociation, but it's not going to dissociate all of it. So let's say, for example, I'm going to take the concentration as 2 here, 2 mole per dm cube, and the degree of dissociation is only, say, 0.02. That's very little. Okay, so the change, this C here would be C alpha, which is 2 times 0.02. So if the change here is 2 times 0.02, the equilibrium for H plus and A minus is going to be that as well, 0.02 times 2. 0.02 times 2. So this is an example. This is how we calculate. And what's left behind is C multiply 1 minus 0.02, which is still almost C. Because 0.02 is a very small number. It could be even smaller. It could be like 0.003, something like that. It's very small. So 1 minus a very small number multiply C, it's still almost C. So your final value for this is almost like the initial value. Because this is a weak acid, it dissociates very little. But you will get a value for the H plus and the A minus, which is also very small. Okay, if you haven't noticed, if I have that much of HA and it dissociates, no matter how much it dissociates, my concentration of H plus and A minus is going to be the same. So no matter what value it is, so I put C alpha here, C alpha and C alpha, so it's going to be the same value. So I'm going to put here Ka equals to H plus squared, because these two are the same value no matter what, no matter how much it dissociates, whether it's higher or lower relatively for the weak acid, it's going to get the same, you're going to get the same value for H plus and A minus. So I'm just going to put H plus squared here because it's the same value. And over the initial concentration, the equilibrium concentration, but it's almost like the initial concentration. So I'm just going to put C here to simplify it. So it's actually C multiply 1 minus how much it dissociates. But then since that figure is so small, it's almost 1. So C times 1, that would be almost C. Okay, so I'll get this formula. So Ka equals to H plus squared over C, which is C, you can get it from the initial concentration. Okay, now my focus is to get H plus, because I need to calculate H plus and therefore the pH value. So I'm going to turn it around. So my H plus would be equal to, so I take Ka, bring the C over, and that is squared, so square root. Okay, so this is an important formula. Okay, so similarly for base, so we're going to use everything the same, except it's for base, the base version. So H plus here, I replace it with OH minus. Same thing, squared over C. So I'm going to develop one for this. OH minus, this is to calculate POH, equals to KB multiply C square root. So it's actually the same thing. If you know how to derive one, you would know the other as well. Now let's look at the question. Calculate the pH of a 0.1 mole per dm cube solution of ammonia, given that the Kb is this. Okay, but ammonia is not an acid, so I can't directly get pH here. I'm going to have to go with POH first. So to get POH, I will need my concentration of OH first, which I can use the equation we had just now. So OH equals the square root of KB times C. So I'm going to do just that. So KB times C, square root the whole thing. And I got 0.00134. I'm going to leave all the numbers there. Okay, and now I need negative log of OH. That is my POH. Okay, I got 2.872. Okay, so knowing that POH plus pH equals to 14. So I'm going to take 14 minus this. So my pH is 11.1. Okay, the next question is about acid, but it's the other way around. This time they give you the pH is 4.5. Okay, and you need to calculate the Ka instead. So pH is 4.5, and you're going to use Ka equals to H plus squared over C. So this time you want to calculate the Ka. Okay, so I'm gonna need the H plus first. So from here, I can get the H plus. Okay, calculate that with a calculator. Okay, so I'm gonna replace this value here. Square this and divide this. Let's key that in our calculator. So I got 2.00 times 10 to the power of negative 8. That would be my Ka. So we can conclude that if POH is smaller than pH, so it's a base solution. Okay, and if the pH is smaller than POH, then it's an acidic solution.